Okay, welcome everybody.
Good morning.
Good morning. Yes, how's it going? All right, so today, sorry, let's connect this up. Today is an opportunity to look at plane stress from a different perspective. So the last time we met, we started talking about combined loading. And we were looking at normal stresses, shear stresses, and in fact, we're typically looking or selecting a plane on a material element. So a material element obviously has 6 sides, 6 faces, and then we're taking a side and looking at what's happening on that plane. Today, we're going to cover what happens when you're looking at a plane of stress and you decide to change your perspective. In other words, you reorient or you orient that plane by some angle. And then we look at the new state of depicted stress for that given orientation. And now you're asking, why in the world would I want to do this? Why do I care about orienting or reorienting an element, right? So you start with something like this, where you have a nice element with your sigma x, your sigma y, and your tau xy, and then we say, hey, let's go ahead and let's rotate it by some amount theta. This theta typically we define to be in the counterclockwise direction, which is following the right-hand rule. You'll see examples, though, where we take slices and those angles are oriented a little bit differently. Maybe it's not a positive counterclockwise orientation, but it's a clockwise orientation associated with a negative counterclockwise orientation, right? So if I end up rotating clockwise by 30 degrees, that would be something I consider to be theta equals minus 30 degrees. Now, again, that's the question. Why? What do you all think? Why would we even spend time thinking about orienting an element of stress by some angle? Why would we do this?
Because you can find like shear stresses and like welding or when you rotate it.
Yes, exactly. So it turns out there's a duality. Before we said normal stress or shear stress, one or the other, pick it and just describe it. What we're actually saying is a shear stress can have equivalent normal stresses, or a normal stress can have equivalent shear stresses. And when we discuss how materials fail pretty soon, some materials, the ductile materials, the ones that are more pliable, those materials, they fail primarily because of shear. There's sliding involved between planes of the material. And the materials that are brittle, that are glassy or ceramic, those materials, they actually break because of normal stresses. So because we have different types of loading, normal loading, torsional shear stress, bending moment stress, or bending stress, transverse shear stress from bending, what am I forgetting? Pressure vessels. Those different types of loadings can have a different effect on whether or not material breaks based on the type of material that you're manufacturing, you're fabricating your structure from. Okay, so that's one of the big takeaways. The reason we care is because sometimes shear stress dominates material failure, sometimes normal stress dominates material failure. And by looking at different orientations of an element, we're able to identify where we have maximum normal stresses at which orientation and where we have maximum shear stresses. Okay, that's the big takeaway. One of the takeaways for why we do this. Because it's not trivial and it's actually kind of tricky to figure out. my big tip for today, if you take nothing else from our time together today, okay? Oh no, is it busted? Something happened. That's not good. That's not good. Oh, okay, it crashed. No, it didn't crash. Okay. All right, here we go. Yes. The big takeaway for today. For calculating equivalent stresses on rotated planar elements. What is it? And you'll hear me say it in the videos. Exaggerate the angles. All right. This is all. Well, it's not all I can say, but this is probably the biggest source of confusion when we calculate what the stresses are on different selected planes. In other words, if I start with an element and say it has that state of stress, and I say rotate by 45 degrees. About Z. I can do this. I can go, hey, that's 45 degrees. All right. And if I look at it, that's more or less 45 degrees. All right. So I look at, okay, my new, right, this is about 45 degrees. So my X went from here, and now my X prime is in that direction. Don't do that. Okay, what I highly suggest is that you rotate by a smaller amount in this case, okay? Make it so that you're just barely rotating. Oh, wow. Okay, so that the angle, even though it might be specified at, this is your angle of rotation. Make it so it's just a little bit. Why do we do this? Okay, because when you start slicing and dicing, it's much easier to figure out whether you need to use sine or cosine if your angles are exaggerated. Okay, so here, if we rotate this element by that amount, okay, what are we what are we looking at? Well, we're looking at, okay, a situation, okay, this is probably better, okay, where, okay, this was rotated by 30 degrees. Now I can take a slice, and this is 30 degrees, but it's exaggerated. That's probably more like 15 degrees, right? That corresponds to this counterclockwise rotation. Right, so you can see more easily, right, which angle is which when you start doing your triangles. Okay, so let me just, I'll point this out. Maybe I'll come back here. So for something like this, it's been rotated that amount, and now if I make my triangle, I exaggerate it greatly. Okay, and this is the X prime direction, so that's the X prime direction. Okay, where's the Y prime direction? Y prime is along this face. Okay, and this was the original x direction, okay? And this angle here is the same as this angle right here, like this, okay? So it becomes obvious, right, that this side, that's the sine face, and this side is the cosine face. Okay, I don't have to think about it much. I just know, oh, this is this is the shorter one, and this is the longer one. Okay, so when you do these problems, exaggerate the angles. It's okay if you waste some space on your piece of paper. Now, you're probably, once you get into the third part of today's session, okay? Actually, it's the second part. Once you get into the second part of today's session, you're gonna find these equations, and you're going to use them, and you're going to like them, okay? Because they make it so you don't have to do all this slicing and dicing. Nonetheless, please be able to do the slicing and dicing. If you look at exam 1 from 2020, from last semester, from the spring semester, it wasn't a big question, but it was a question that involved having to do slicing and dicing. The slicing and dicing allows us to keep kind of a fundamental understanding of what it means when we do these rotations. Okay, so you should still be able to do the slicing and dicing. And it turns out, you may love these equations right now, but once we do more circle, you probably won't use these equations very much. Okay, you write them down on your formula sheet, but you will have another technique, a graphical method, that allows us to be able to calculate the equivalent stresses with rotations without having to use all these equations. Okay? And it can be very fast. It can be very fast instead of plugging things in here. Okay? So that's all for now. You can go ahead and start working on the videos and the questions. Something to keep in mind, I guess, is that we moved the deadline for the previous assignment to per our discussion last time we met, moved it to the end of this session instead of the beginning of the session. So maybe that will give us more time to discuss what we discussed last time. We're still going to, keep going though with the new content at the beginning. All right. The other thing is, after how many years of using Canvas, I figured out how to weight assignments appropriately. So now if you look in the Canvas grades, you should see that everything is weighted according to what is on the syllabus. It wasn't that hard. I just never had learned how to do it. Okay, so even us, how do you say it? Old people, or not old people, but those of us who might be a little less, have a little less plasticity in our brains, we are able to learn new tricks.
Old dogs learn new tricks.
Yes, yeah. Yeah, the technical term, right, is neural plasticity. All right, so that we're like able to, you guys have a whole lot of that, which is great. We all have some, but to be young again, to be able to absorb and change more quickly, we can only wish. Those of us who are getting up there. All right, great. Go for it. Questions? I'll be happy to answer, and I'm around. Yes, Mark.
I have a question about question 4.
Okay, on session 16, I'm taking it. Okay, hold on. Let me pull up my pieces of paper so I can see. Ah, yes. This is a nicely involved problem. What's up with it?
I was just wondering, do we calculate the applied moment the same way we calculate the applied torsion, or is there a different
So do you calculate the phi? Say that again?
Because there's a flight torsion and a flight rolling, right?
Applied, yes.
Yeah.
Okay.
Torsion is in the positive direction, and then the moment is in the negative direction. So
Yes.
so the calculator, would you just,
Well, so, I mean, this applied moment is actually in the positive z direction, right? You see, it's coming up around,
is it on the x?
it's on the z, right? Yeah, it says NF is in the positive z direction,
Okay, so,
right?
Okay.
Okay, so in this case, right, we're looking at shear stress, right? So, an applied moment, by itself, we don't think of it, usually in terms of creating shear, right? We're looking at bending stress for the applied
Por
moment.
ejemplo, si tú tuvieras un punto acá, sería cero.
Okay.
Hay una línea. Tienes que
So applied moments, right, because, I mean, if we just go back to the equations, right, because
si está arriba es cero porque no hay área.
so this applied moment is, okay, so there are
Si es
4 loads on this, right?
tú sabes
There's
que
PZ,
si la fórmula que es
EX, and TF, right?
y
So PX is acting on the side in the X direction, right? So that's a normal,
si está justo,
right? That
si está justo
probably
está
is
arriba
affecting
del
a shear stress,
si está arriba
okay?
PZ
es cero porque esta fórmula de
Yeah,
acá
PZ can affect it, right? Because it's at the top,
y no hay área.
where A is the location, right?
No hay
And so
área.
PZ is going
Entonces esto va a
this
ser
direction,
esto va a ser
right? And
cero.
where's the transverse shear stress maximum?
Justo en el borde.
the max radius.
Es el límite.
No, transverse shear stress, so bending moment, bending stress is maximum at the outer surfaces, right? But transverse shear stress is maximum at the neutral axis,
Oh, right.
alright, because you get the most, well, you get most VQ over IC, right? That's kind of circular reasoning, but, so the PZ is going to be affecting the shear stress, right? If I take a face, it's going to be affecting it in the, it's going to be in the Z direction, but on the X face, right? So that's relative, because that's what we are determining shear stress tau XZ, right? So that is going to be, that PZ affects it.
Yeah.
Okay, what also affects it, well, MF probably not gonna affect it, because it's just causing a bending stress, right? It puts A in compression, actually. See that? A is on the top, so that bending stress is gonna be, right? So this is like an F, right, and it's like this, and so it's causing the top to go into compression. That's a normal stress, so it doesn't affect the shear stress. Tau at, or T at, that definitely affects the shear stress, right? And so, if you think about that T-app, right, it's causing these these circumferential shear stresses, right? And so now I gotta go to the top, and that's a max there, right? So that's gonna be a TC over J, right, acting in the XZ, acting on the X face in the Z direction.
So for this problem, only PZ and the TF affect the shear stress.
Yes,
Okay.
yes. That's right, I just wanna make sure that I'm saying that correctly, yeah.
But it's because like it's relative to this X plane, right?
Right, so remember, these, the way we did, it was good you asked in the group meeting, right, last night? Remember, the first subscript for these stresses, especially the shear ones, right, is the face it's acting on. And then the next subscript is the direction, okay? Now, it turns out that tau xz is the same as tau zx, right? But here, I'm not, and so you can think, oh, is it easier to think of the X face on the Z direction? Or is it easier to think on the Z face in the X direction? So it's like,
Hypothetically, if we like want to find shear stress on the on the Z plane. So when you're doing a surface, it's the Z plane. And then take into account and app instead.
So, yeah, so let's say if you, so MAP is only applying bending stress.
Oh, so you
Right, it only is here, okay? I mean, you can have, like PZ is applying both a bending stress and a shear stress, right? Because that's the transverse load acting on a beam, right? PX is only applying a normal stress, and TAP is only applying a shear stress. And so MAP is only applying those bending
So you just
stresses.
ignore it.
Yeah, you just ignore it, right? That's part of the name of the game, is knowing which one's going to. Alright, good. I'm glad you asked that question. Alright, so that should make it a lot easier.
Yeah.
Because you only have to worry about two.
Hold up.
Okay. Okay. Bless you. Okay, I just took attendance. Okay. C. All right, so I've gotten a chance to meet with almost everybody, almost not everybody, but about their exam one. But Jason, let's talk for a sec. We'll go to the other room.
Okay.
We've been doing this. All right. This room will be available. Any questions? All right. Hey, how's it going, Michael?
Good, sorry, Marie.
Okay. Yeah, and thank you for sending group me messages last night. I appreciated it. I'm sorry it took me a little while to get to them. But, and if I didn't get to your questions, sometimes like it was good. There was a lot of discussion. Good. So if I missed someone's question or it didn't get resolved automatically, just send me another message. All right, and I'll try to do that. It was good though. It was good.
Can't leave my man Mike hanging.
Yeah, I got it. I understand. Yes.
It's about the exam.
Okay, yeah.
What sessions will we cover in the exam?
Okay, good question. All right.
10 to 20?
Yes. So it's going to be that's you answered the question. So there's just a question about the question on the exam.
What's the exam? What's the exam?
Right. So the exam is a week from today. All right. A week from today, and the exam will cover through session 20. All right. Absolute max shear stress. Okay. So. So just a note on, these are extra ones. So note on exam 2, material through session 20, which is on absolute max shear stress. So, yes, this session 20, the homework will be due on the 27th. Okay. And the plane strain, more circle, that homework will be due the day after the exam, at the end of class. Okay, so you have the 27th essentially, right, to focus on preparing for the exam. And if you really want to get ahead over the weekend, right, there's nothing keeping you from just going through these. That's the plan? That's the plan, okay. It's all up there. And in the group me, feel free to ask questions, you know, going way back if you like, you know, about previous sessions that were not clear, all right? You can also go forward, but you probably won't get as many responses. I can respond to those as well.
No question.
Yes. Yes, Carlos.
This is a big question, but I got stuck, so like finding here.
Okay.
Got to talk about like integration. But I don't know if I.
Okay. So you have the stresses, and so now we're estimating the angle rotation. We have, okay. So what I would suggest is actually to use the COLAB. Alright, so for this, See this? So what this is essentially an opportunity to plug in your values, and then you can test. You can put in different angles, okay? Or you can look at the plot and see where theta goes to, or tau goes to 0, okay?
Okay.
So the way to do that, I mean, I can just show you right now, right? Is you just Control Enter the first one, okay, and then if you go down, right, to here, Control Enter, okay, and then what it does it gives you the plots, right? And look, you're looking at a tau xy plot right here, right? And your estimate is, the question is, when is it equal to 0? So now you can estimate the angle. So you can plug in your own values, well, the values you're given in Canvas, and plot it this way. Okay? Yeah, so I didn't expect everyone to, I mean, you can do it. There are other ways. Well, when we do Moore circle, there are other techniques to get it to 0, okay? But this is what I was getting at.
Okay, yeah, I didn't check the.
Yeah, well, that's why we're here, right? That's why we're here. We asked the question. Maybe in the problem I should have said, I could change it to say, you might check the collab.
Okay.
Maybe I can do that. I don't mind doing that. That's is that number 3?
Yeah.
Okay.
Excuse me.
Yes, just give me a second, okay? I'm just. Hello, good morning. Okay, great. So just so everyone's information, nothing is wrong with session 17, number 3. Nothing's wrong with it, but I just added a hint that you might use the collab for this question to be able to solve it more easily. Okay. Yeah, that's all.
What's the direction of the slides?
Yeah, I just
Don't understand.
okay. So
I know that it's supposed to be the face.
right. So this is the x direction, right? And so that's and tau xy, right, is on the x face, right? So x is orthogonal to that surface. And then
This
it's
line's
in the,
supposed to be to the positive.
in the Y, yeah, it's in the Y direction, that's right. Because this is the X face. This is because it's coming out. That,
So what
that's
about
back
this
face
one?
is actually the minus X face. Okay, so on the back side of the cube, it's in the minus X direction, all right?
So it's
And
also to the negative.
it's also going in the negative, exactly, all right? So early on, we did some equilibrium and we said that tau xy is equal to tau minus x minus y.
What is tau?
Shear stress.
Oh, I mean this symbol.
Yeah,
Oh,
that's
okay.
tau.
I just.
Yeah, oh, yeah. Yeah, yeah, that's right. Is that cool?
Yeah.
Does that help?
Yeah.
Okay,
Thank you.
sure. Okay. George. He's on his way? Okay, what am I doing? In the road, you that's here. Also, so there's something I already told everyone, but if you can relate, a couple of things.
That's fine.
One for this, make sure you use the angles. It's, if you look, I wrote 2 notes on the OneNote about that. I guess also I talked about why it's important how we even do this, is because some materials that are ductile fail equal to the shear stress topic. Other materials that are real fail because normal stress is topic. So this is an opportunity for us to look at what is kind of the equivalent normal stress and equivalent shear stress. Okay. The other thing is, after many years, I'm using data to figure out how to use their weighting. So now, yes, I know, you can teach an old person new tricks every now and then. It's actually not that hard, I just didn't know how to do it, okay? So, so now your score should be weighted appropriately based on the syllabus, okay? And, yeah, exam 2 is
The negative.
Yes, 2t over session 1 times 2t.
that's also on the plan.
Oh,
It's on a Wednesday, right?
It is.
I forgot to, okay, so how much?
4
E?
3
Here,
times.
let's, yeah, let's,
Yeah,
let's,
that's
fine.
You're a positive value rate.
Quedó con
That's the exact same.
That's all the exact same.
ahí eso no me dio idea. Pues ahí no me dio.
Yo recién enseñé.
Oh, actually, no, I don't think it's for chemistry. I did PX, so that's why.
Cuando este cero, que no me da aquí abajo.
Degrees.
Oh, yeah.
Que lo quitara de 10. La mitad de dañar 10. La mitad de
Puede que sea un poco atrás, puede que sí sea 15.
Así es, ok, vamos a poner 15. Mira.
La verdad, yo me hubiera quedado en 20 años más atrás. Entonces, ¿en serio? Me he vuelto un adicto. Yo que sí, familia que sí. Yo siempre abro todos y me dio miedo porque es un proceso. Pero ese proceso está fácil, ¿no?
Sí, pero It was at 20 hours.
First, oh, ¿por qué el código? ¿Por qué no se hace directamente? Literalmente esta es una.
Oh shit, es cierto. Mira, podría haber hecho eso. Ah, no, no, pero lo de ira. Puede ser X.
No me volvió otra vez. Yo recomiendo ver.
Also make a science. I'm a full person mentioned it. So don't forget about it. So yeah, it's trust me. Essentially, oh, the only person for the second one. Oh, or?
I got it.
62. So, well, the first one is multiple choice. I should read the order. You're supposed to do that.
No, no funciona.
¿Cuál es el problema? ¿No has puesto el signo de multiplicación, Carlos?
No, creo que ya se puede.
Yeah, but here's what.
Perfect.
¿Por qué pedir el tema?
No.
No, pero control C.
He's increasing, he's augmenting his understanding.
I was trying to like plot it into Desmos, like the same graph.
Sure.
But
Yes, he then like he deleted it.
I did like everything, the long formula, and I did it like I don't know. No, you cannot do it on that.
Well, the difference between MATLAB and Desmos, or the difference between MATLAB, Desmos, and Python, there are kind of two ones that kind of continually hang out with us. One is the exponent, right? So Python it's asterisk, whereas in Desmos and MATLAB it's going to be the little caret symbol. So that's one, and then pi, right? Normally you can just define pi, but the way we use numpy, you had to np dot pi. All right. So if you find those things, that's probably helpful. But then, of course, the plotting commands are a little bit different, right? But in terms of just the equation, I commend your, at the same time, I'm like, just hit Control Enter, for goodness sake. Just hit Control Enter, it does it for you.
Yo lo configuré inicialmente. Didn't know this was Python.
What's that?
I didn't know the calculator.
This has Python. I didn't know.
Didn't know.
Wow.
Yeah, I got the cross product, the dot product, I got the differential product.
Okay.
It had, wow, I didn't know they had, which calculator was that, a TI?
Yeah, well, it's.
Oh, yeah, it says Python.
Yeah.
Yeah.
I don't think
I
you have
remember
like
my
that.
calculus, like, for my homework, because you can use it in exam. So I had the cross product, the dot product, the quadratic formula, I just wanted to say something. That's it.
Yeah, well, you can bring a formula sheet into these exams, right, so, or a sheet of notes, but it's, so. I don't know if it makes sense to put everything in memory, but. What's up?
I have a question about 16, right? So, you have to calculate the shear and the torsion.
That's right, right, the center shear stress from which one though?
From point A.
Okay, so the A is the location we're interested in, right?
Oh, excellent.
Yeah, so which of those forces?
Like, if there's no power.
Oh, wait, this is Q3. Okay, yeah,
It's not
different. Not 4, okay, sorry. Yeah, okay. So, in this case, right, what could be causing? You really only got one option, right? Transfer You did, right? You got what, you got P.
Yeah.
Okay, right?
Exactly.
Okay, yeah, okay, now I see, because you got,
So my problem is, well, for the first term, the torsion, my units, well, first of all, my main problem, my units here are newtons, my units here are Newton meters squared.
okay,
If I identify it, that seems like you can't do that.
okay,
I can't really
so,
because you're supposed to test it.
so this should be,
But you remember it, right?
Yeah, he was in my, physics, 2. Okay,
Yeah, so
this should be,
given A, wherever it is, yeah, we don't know A.
okay, so,
So I figured maybe I could do this.
you do know, so, whoa, yeah. Yeah. So first, what's the equation, let's write out, what is the equation for that shear stress? For torsion?
2 PA pi C Q.
No, we're doing, that's a torsion problem, right?
Okay.
It's TC over J, right? So, yeah, that, I'm not sure what that is, actually. But it's, that one is this TC over J,
Okay.
alright? So it's gonna be your tau app times C over J.
Okay.
Right, now, there's
I
another,
got that from,
Oh, yeah.
this, so this magnitude is correct. Okay, because that's the 4/3 right times the average. So you got that right. And then this is gonna be the TC over J, right? Now, something that's missing though is a drawing. Okay, which direction is the shear stress caused by P? And which direction is the shear stress caused by?
So I really did that.
Right.
Like that little bit bigger, like adds up.
And they're not much bigger than ours also.
Yeah.
Four times bigger.
That's correct. That's correct.
You just spend.
And we're at the top, so we're at the top.
Also, they never used to, like, it's
A new set.
Right, like at the top. No, it's fine, so just put it down, that's the point.
You know, like you could literally fit all our machine.
Like just put it at the top.
like I kind of bring it on the.
Just look at it, it's fine, this one you can do looking at it as a cylinder or as a circle, right? So it's at the top, so location, how do you use the stress that we're interested in is at the top.
And a GM show is there for a reason.
You have to like find like.
That's fine, I would even keep it simple,
Also,
it's
like
just, it's just draw a
It's
circle.
Plug it in.
Plug it in and then.
Yeah,
Yeah, for that is, so just draw the circle and say it's at the top. Okay,
Our welder can even get
Now.
I know.
yeah, okay, now there's a little that's up there, P, right?
Figure it out.
So just draw P. So the way you break it down, right, is you say, okay, you can kind of do like a superposition problem. What is the shear stress due to P? And what is the shear stress due to T app? Okay, so this one, let's say this is the T app one, right?
Yeah.
So draw for me, which direction is the shear stress going from T app for torsion? On that same circle.
Shear stress due to torsion.
Right,
For TF.
because of T app.
That's a TF.
Yeah.
It would be something would just be vertical without the axis.
That'd be horizontal. So it's at this location, at that location first of all,
Okay.
right? And so, remember how the,
Would it be like
that's transverse shear stress, right? So look at your notes, what does the stress look like for torsion? Keep going, it's back a ways, it's back a ways, it's back a ways. No, this is a rod. It's twisting the rod. Okay, that's. Okay, so what is it? It looks like, maybe I'll borrow your pen. Sure. Okay, when you have, wherever you want, well, maybe on where you're actually doing the problem is a bit though. Where's the problem? On the beam. Okay, so with torsion, what you have here is we're applying a torque. Okay, and let's say it's about this x-axis, right? So remember we said before we have like shear strain, we have shear stress. And so if I were to take a line here, right, it starts very close to zero and then it becomes bigger. As it comes out here. If I'm at the top, then it's big here. And it gets smaller as they go in, right? Because the other equation is that
it's max at it's max at J equals C, or yeah,
just where rho equals.
rho equals C.
Okay, so in this case, remember, we're interested in tau xz, which is on the x face, it is in the z direction. Okay, so we could say that tau xz due to torsion, right, this is just going to be that TC over G, that is positive. Okay? Now, what about transverse shear? Transverse shear is a little bit true. So that's torsion. Now let's look at transverse shear.
Wait, why is it positive? It's in the direction of Z axis.
Right?
I guess that's true.
Yeah, it's
Although-
Z, right?
Do I just have to define like this way is Z positive instead of that way?
Well, I think I came out in the notes or in the group meeting last night, right? To figure out where Z is, it's X cross Y.
Oh, so it's just right here.
Right, so which is in, the Z, it's going to the left.
Yeah, makes sense.
Alright? Now, for transverse shear, that one, the transverse shear, it's a max
Yeah.
at the neutral axis. But look, the shear stress that's being induced is from P point to this direction. So it actually is like this. That's another minus.
Okay.
Right? So that means that we have plus, now it's equal to subtract the transverse shear.
Okay.
Okay? Try that, because it's in the opposite, so you gotta draw these pictures. Make it easier.
I don't want to be because this is my company's charging me extra. How much is the bill? I'm not gonna ever get this, but I'm gonna do it. So I guess I'm just thinking this side.
So I skipped, so Owen?
Yeah.
I kind of made a jump, right, to being able to say that the transverse shear stress is in that negative direction, right?
Well, it's because P is pointing in that direction.
Because it is true, P is pointing that direction. Remember, transverse shear stress comes from the internal shear force. So you might take a moment and just bend your mind about that, like, okay, what is really the internal V, right? Because it's V that does it. And so you can convince yourself that, yes, if I expose that face, V is actually in the same direction as the T.
Okay.
Yeah, just pointing that out. Okay, sure. Let me just hold on a second. Welcome. Okay, we're good. I think everyone's marked here. Alright, what's up?
Question one, doesn't matter, so we have equal transformations and x options, right?
Okay, so
Doesn't matter which one we decide next one. That's just two count, about count.
Okay, so this one is okay, so no, it shouldn't matter too much which one.
And that's one, what's that one, right?
Yeah. The other thing is that this is a 45-degree rotation, so if you want to write down there. Yeah. But tau, yeah, but you're right. So tau xy and tau yx are going to get.
Bigger than the size of Bush campus?
Doesn't have, this is the first 2 gigawatts over 1 average. Why? Yeah, that's like, yeah.
Oh.
All that. So then you also do that, you can't wait there for about 3 hours.
Yes, what's up, Carlos?
For the last one, I'm kind of like thought that when they rotate the wheel, right, or just like one plane.
So we rotate, so we're rotating 90 degrees, right? Let me just make sure I read the question. Oh, yeah. Okay, so, yeah, this is hard. This problem is super hard, yes. Again, you might wanna use the Colab, alright, if you, yes. Right, cause you're doing, so we're doing a rotation, right, and then we're doing another rotation.
Second two rotations.
Yeah. Well, I don't know.
So what we're saying is, okay,
Yeah, we can do that.
What is the magnitude of shear stress?
Yeah.
Element rotation.
so this is just a,
Oh, that's why. It's supposed to be.
So I'm just gonna write this down and start to see what like that, so.
let me make sure I got this, let me read it, it's hard for me to read. This is there we go. Yeah, okay, so. Is there more than one problem? How many problems do I have? It's just, oh, those are the, okay, let me pull it up. So I don't have it here. We're rotating about the X, not the Z first. The X, not the Z. That's the first thing. Okay, let me just make sure that.
That's really everything. It's less depression.
Yeah, so it's the first question, right, is saying, what is the resulting sigma x prime, right? If we rotate an element about its own axis, does it change that axis?
No, it should be,
It's the same,
It's the same,
right?
yeah.
So that's the point of the first question, okay? So that one, right,
should be the same.
stays the same, okay? Now, the second question is, we're rotating about the x-axis. Now, what we're asking is, what is the resulting tau x prime y prime? Okay, so in this case, all right, we've rotated, okay, and this is, so you have this, and then we're rotating 90 degrees, yeah,
So it should be the same magnitude but opposite direction because
correct,
it will be in the top, right?
correct,
That will be,
that's right, so it's the negative,
okay.
okay? Yes,
Then for the C, like how do I find this sigma C prime? Because I don't have any information on C.
okay,
Oh wait, it will be in the negative Y,
yes,
you rotate it. So it will be negative 100.
yes,
Okay. I think I got it.
okay,
Then the sigma Y will be in the original C, but then the original C there's 0.
yes, you got it,
Okay,
you got it.
thank you.
It's a mind bender, right?
Yeah, yeah. After I drew it, like I actually like I think of the geometry.
Good. Good.
So for question one, section 17, we have a cylindrical pressure vessel.
Yeah.
And then if you want to take like an element, just like, you just take it as a square off of the surface.
That's very nice drawing, yeah.
So then if we incorporate that here, it would be group stress this way, and then longitudinal stress.
Okay, so, if you take that orientation, that's fine, yes. So the stress is still, group stress is in the Y in this, right? And that's the way you've drawn it, right? That's fine, right? And we're asking for shear stress, right?
Yeah, sure.
Okay, so now, what we have to do is we have to take that element, right? And rotate it 45 degrees, right, to be able to get new shear stress. And new
That one,
orientation.
So we have to use like one of the stress classifications.
So for the first one, I mean,
You're right.
you do the
A
triangle.
is area is 2A and B.
Oh,
Right, right.
It's fine, you find what it is.
because we don't,
What do you mean,
Right?
we don't have that's why sure.
M can be,
Okay.
Yeah, that's what I was hoping, but I understand
it's
you want it to do differently.
It's A squared over E times 2A. But it's very cute, but overdrawn. Because I is, at least the L and H is 2A. So Y is 1A.
Oh.
So for the area is 2A times B. And for the I, it's 2B cubed. I'm sorry, 2A.
I said A.
Also these things.
What was your simplified formula?
For what?
The whole thing, U over A, negative Q over A, minus.
So,
Times 2A cubed. Y is A squared.
So essentially, you are rotating on that line now.
Oh, I just, okay, I see.
And so it's PA, I'm worried about that, what's A for Y? That's all.
Dr. Maxson,
Yes.
without the rotation, what do you find saying that? How do you find, talent?
So what do you mean without the rotation?
Like meaning like it's not right.
Okay, so you start with initial state of stress, right? And that initial state of stress has no shear stress on it. And you hammer that in rotation, it still has no shear stress. Okay, but once you rotate, okay, then that's when you perform the equilibrium to see what that, if there is any shear stress that's developed.
But when that's easy pressure, also there'd be a shear stress even if it was just in line with the boot. So no.
So in a pressure vessel that you have a circumferential hoop stress and you have a longitudinal hoop stress, right? that's why we do the triangles, right? That's why what we're saying is, look, if you rotate,
Isn't it just the same pressure vessel, just like?
that's right, same pressure vessel, same location on the pressure vessel, but now I'm looking at an element at that location with a different orientation.
No, I did that, but then how come there's a tau XY in the stress transformation?
Just a quick question.
What do you mean?
Just
Initially, in the original
I'm
orientation,
trying to find
it's zero,
tau
but
x.
when you rotate it, it's not zero.
Dendron is right, where it's tau x,
Right.
so.
So don't use the stress,
Like,
before you jump into the stress transformation equations, right? Look at what's happening with the triangle. When you take a slice, right? We said, okay, I had,
Yeah.
because I can start with a
X,
2D state of
you want
stress.
tau on the X
I
plane,
could have a
and then
tau,
you see
like
the
I
direction.
have sigma x and
I
then
think
sigma y, right? In this case, tau xy is equal to 0. But when I rotate, right, the element, and I still want to maintain equilibrium on the element, sigma x changes, sigma y changes, and tau x y changes. You get what I'm saying?
Yeah.
And if you watch The Efficient Engineer, they talk about how these stress transformations, right, are, and this is a confusing topic, right? But the, and what we're looking at, as we said at the very beginning of class, the objective is to be able to figure out what the equivalent shear stress might be in at a location when you have, normal location, or what is the equivalent max normal stress. That would be
ahora hay transfer.
that you have shear, alright?
The wall thickness here, that's just to.
¿Qué pasó?
Dale, ahorita te vuelvo.
Pero este no está cancelado.
¿Quieres que ya sabes?
No, creo que si subo y me voy atorado. No, mejor no subo ese. Me voy atorado. Subo en la parte de atrás de mi bici.
Yo ahorita no practiqué.
Eso es mucho.
Todo no practiqué en la máquina. Va a tardar.
Yo, ¿sabes? Mi plan es llegar rápido. Yo sabes que
Primero se ha inspirado de pero está
¿qué importa? Yo soy curioso otra vez. No hice nada.
yo te compré equivocado, pero no hay constancia.
Y por eso una vez compré que era de luz de la Elizabeth y salió más barato. No, una vez compré boleto para Linde, yo otra vez. Eso es un montón. No puedo hacerle mucho tiempo.
right? The lowercase
Like the
considerate.
big letter A.
Yeah.
and it's delta.
Just more of the. Right, yeah.
Maybe why do you do two A instead of just A B? Oh, two A, okay.
Oh.
Yeah, this is, oh, okay. So there's
This is zero, so X and Y have to solve those as
I'm tracing that. This just goes next direction.
This sounds
It's just big with the box. Repeat that.
Later, later.
prefer that you do it with the triangles.
Okay.
So first is, yeah, but I think, so why don't you draw the triangle that describes what this new state of stress is.
Okay. Doesn't make it too
You draw.
Right. So, how do you do it? So it's, that diagonal line is the new line, the vertical one is the original one?
Yeah, so if we go back to this drawing that you have, that you
Here?
did,
The
right?
original one.
The original, right?
This one? Yeah, okay.
So we're saying, what is sigma x prime, right? Here, so if you were to, so draw the original thing. And again, we want to make it exaggerated. So this is drawn at 45 degrees,
Okay.
which is not exaggerated.
Right.
So draw it super exaggerated.
Why is that?
That way you know which one is sine and which one is cosine.
Okay. Better?
Sure. Okay, so now, this was your sigma x, this is your new sigma x prime direction.
Okay.
I mean, normal opposite.
Yeah. So,
Okay. Okay, so now the question is, right, that angle in there, right, that's 30.
that's 30?
That's
20?
Sorry, 20, yes, it's 20. Alright, and so now you're doing your triangles, you know, right, now you go back to the other diagram, right?
I see, that's that angle as well.
Right, that's the theta, right? That's the theta. My guess is when you're doing your transformation, it's put in 7.
Oh, yeah, okay, I see.
It's not 7, it's actually 20,
Okay,
right?
okay, thank you.
But you should still be doing the triangles.
Okay, also, one more question. There's also issues with this one.
You should be still using triangles.
So it means it's 45 is this, so it matters, for sure.
You can use the transformation, that's not the point. You can use the transformation equation, to get the concept down, you should use your triangles.
49, you're exactly 45, right?
Again, it's one,
You can close that time, you can.
that way you get it, you understand which one is the math.
Okay.
Alright, so in this case, that's just making it exaggerated, right? Okay.
Right,
You don't know. That's why I'm asking you to use that. Right? So we have, what is your stress? Yeah, so which way is so you can draw the diagram, right? Okay, you got a pit.
No.
Which is gonna be your
and
x.
X is pure, and X is pure.
Okay. Alright, so drawing the cylinder, right? Which
Hoy que me
you're
tengo
saying
que
is-
quedar, que puedo estudiar.
Okay, sure. Yeah, okay. Okay, then show me which is x and which is y. You said you want P over T, so yes. The stress is higher, right? This other one, that one will be
Tiene que limpiar.
yeah, so that's right. So now we're saying rotate that element, y that amount.
Yeah.
Okay. So everywhere. So yeah, so draw sigma x, draw sigma y. triangles to be able to figure out what the new sigma was asking for the shear stress, okay? So you have to have a shear stress rate that goes on here as well. That's going to be your tolerance by y prime. So go ahead and draw that.
Yeah, I'm experiencing square.
You don't even have to finish the square here. It's just along the surface.
Okay.
Right? This is the y prime direction. This is the x prime direction. So it's tolerance.
Right. Get that off of this.
So the triangles, right? So you have to figure out what the a's are.
Sure. No, está ahí.
Pero ¿por qué lo hacía el músico?
With the direction,
Están-
yes.
están
It's on the
cancelados
area
todos.
side, it's on the area aspect.
Pero mira el otro bastante bien.
So the area is going to use the
Yo puedo ir tranquilito. Porque sabes si yo podría llevar
This
atrás, ¿no?
space, right?
yeah.
Like this angle is the angle we're using.
No, sería
It's on our
complicado.
basis.
Además ahí voy con la mano.
Again, we just throw theta in there. So is this space, what's the area? This is the hypotenuse, that's your original delta A. So what's this space?
That's going to be the cosine of A.
That's right, cosine of delta A, that's right.
Cosine delta A.
This is gonna be sine, right? That's why we draw this exaggerated. One of the reasons, so we know which is which.
Dice que el otro viene a 2.53.
Now, which direction is acting, you want it to be acting parallel, right, to the x prime.
That was particular. That was particular.
Mucho tiempo no sé qué hacer.
Yes, so you have to do them, you have to essentially,
Yo sé ni cómo.
do them
Tengo que
all.
tomar notas.
And figure out which components are in the x prime, which components are in the y prime direction, and then you can live your out.
Sí puedo intentar.
Why don't you watch that video, okay, so that you can get what's going on here. Right? But we need to figure out what this is the y component space. It's acting on the delta A sine 30. That's in that phase, but now I have a component that's in this direction, that's in the y prime direction. So this vector is going to be acting sine theta.
This one, that's the y prime direction, right? That's the
Yeah,
y
I'm sorry,
prime.
this is actually cosine, right? So this is now, this is hypotenuse, right? So this is cosine. And that's why we make it exaggerate. This is a short line.
Oh.
Sí, voy a enviar. No voy a poder tomar notas. Está todo pelado. Esto no es sucio. Es que no he lavado. Yo lavé esto, lo raspé, ¿no?
No, delta A
Pero fue una mala idea raspar.
base of the
Well,
triangle.
Lo pelé.
So for all the triangle,
No le
right?
vi nada de tasado. Especialmente la algo.
This is the delta A. That's delta A.
So it's hard, what is that? Is it the trend, is it the?
Yeah, so
Ya
just
me
like
lo
those signs.
Empiezo a volar por todos lados. Mientras le pego y le tengo
Well, what's down?
unos
So what's
compasos.
the, how do you ever get delta?
Delta A is, you can given that as a value, you're like, it's just like some arbitrary element, right? A cube has 6 sides, each one of those sides has a small area, we're gonna call it delta A.
But it doesn't, in the example question, doesn't give you.
It's you never calculate what delta A is, because it's to be whatever it wants.
You know,
They cancel out, but delta A is always cancel out, it's an infinitesimally small, it's an infinitesimally small element. Yeah, this isn't, I think this is answered in the video if you
haven't lost it. I suggest that you lost it.
This sigma x and y.
Yeah.
So I don't know if I have this oriented right.
Okay.
I don't know. I don't know what sigma x.
So you can choose which orientation you want to use. Okay. So if you just draw a profile view of the sun first. Okay. Just draw a profile view of the sun, right?
That's just practical.
Yeah, just a right, exactly. So draw a profile view of the sun. Thank you. Okay. Yeah, no, take a spot, right? So take one to be x and take one to be y. Which one do you want to be x? Which one do you want to be y?
So this y
Okay,
is
that's an interesting choice.
No, okay. No,
I would do,
okay.
I would do y up, right? Just make it easy for yourself.
Y up?
Yeah.
And that's what I did, but it was down.
Over J, which is
Right. So you're gonna end up having to rotate,
Yeah,
right?
yeah.
So sigma y, what is sigma y in this case?
That's hoop stress.
Yes, which is equal to,
To PR to T.
no,
No.
the other way. The hoop stress is
Oh,
the
I'm
larger.
sorry. No, you're right. Yeah.
Hoop stress is the larger one, right?
minus.
Okay. Not t squared.
It's, I know, it's T2.
Okay.
I had more space.
Okay, okay, so go ahead and write that out. Say, just write next to it, sigma y is equal to CR over. Right, just on the drawing. Just write sigma y, because that's the y direction. Just write sigma y. CR over. Okay, and then what is x? What is sigma x? It's the longitudinal one,
Yeah.
which you just said,
Oh,
so it's
so
PR
it's-
over 2.
Oh, okay.
That's the sigma x.
Okay, is that's what it is? And then if I just plug it in, that's great because the original.
Okay,
sheet stress is
again.
0.
I highly suggest that you do not use the equations on questions 1 and 2, okay? I mean, because just look at the spring 2023 exam. You had to be able to do the drawing, all right? I understand that the transformation equations are very useful. You can use them. You gotta,
I'll try to do it that.
you gotta use the, these questions to do the science, okay? All right, you got it, Mike? I go back. Okay. All right, everybody, thank you for coming today. I anticipate there will be some questions on number 4. So send something in the group me, because it's a little bit difficult to wrap your head on, and I think I also may have made a mistake. So, but I'll update you over the group me, okay? I'll update you over, and we have the beginning of the beginning of the next session. Okay, correct. Okay. If you got it right already, or if you got it right according to what's written, I'm not going to take off points, but I think I made a mistake. But I'll get back to you. Okay.